In the Amazon, the worst pain is not always the kind you can see. It does not need torn flesh, broken bone, or a dramatic kill scene. Sometimes it begins with a sting, a spine, a bite, or a brush against the wrong body. And then the real damage starts deeper in the dark, where nerves misfire, muscles tighten, and the body feels like it is burning from the inside out. This episode explores the rainforest's most vicious toxins and venoms that do not just wound prey, but turn the nervous system itself into the battlefield. In a place where survival depends on staying functional, that kind of pain can be more dangerous than blood. The forest does not warn you with movement. It warns you with pressure, subtle, invisible, and already too late by the time your brain recognizes it. In the lowland Amazon, where humidity thickens the air into something almost tactile, the ground itself feels alive long before anything visibly stirs. Fallen leaves are not just debris, but layered architecture, a shifting lattice of tunnels, pheromone trails, and hidden bodies moving with collective intent. Somewhere beneath that surface, a colony of Paraponera clavata is already aware of you, not as a threat in the human sense, but as a disturbance in a system built on precision and response. Bullet ants do not hunt you. They do not need to. Their entire biology is engineered around defense. Specifically, the defense of a colony that represents thousands of individuals operating as a single, coordinated organism. Each worker is large by ant standards, often exceeding 2 centimeters, with a matte black exoskeleton that absorbs light rather than reflecting it. There is nothing ornamental about them, no warning colors, no exaggerated features. They rely on something far more efficient: certainty. When contact occurs, the outcome is not ambiguous. The colony itself is usually anchored at the base of trees, where roots create stable microclimates and vertical access to canopy resources. These ants are not confined to the forest floor. They move between layers, harvesting nectar, scavenging, and occasionally preying on smaller arthropods. But their defining trait is not what they gather. It is how they respond when that network is disrupted. A misplaced step, a hand brushing bark, or even the subtle compression of soil above their tunnels can trigger a cascade of signals, chemical, immediate, and impossible to negotiate with. The first ant does not hesitate. It does not circle or test. It commits. Its mandibles anchor into the skin, not to tear, but to stabilize. This is not a bite in the conventional sense. It is a locking mechanism. The real event follows a fraction of a second later, when the abdomen curves forward and the stinger drives in with controlled force. At that exact moment, the narrative shifts from external interaction to internal invasion. The venom of a bullet ant is dominated by a peptide known as toxin, a compound that does not simply irritate tissue but directly interferes with voltage-gated sodium channels in nerve cells. These channels are responsible for initiating and propagating electrical signals throughout the nervous system. Under normal conditions, they open and close with precise timing, allowing neurons to fire in controlled patterns that translate into sensation, movement, and coordination. Toxin disrupts this timing. It forces the channels to remain open longer than they should, prolonging the electrical signal and effectively flooding the system with continuous nerve activation. The result is not just pain, it is a sustained, system-wide misfire. At first, the sensation is local, a sharp, immediate spike that might be mistaken for a severe sting or burn. But within seconds, that localized signal begins to expand, not outward across the skin, but inward through the nervous system. The brain receives not a single point of pain, but a barrage of signals that do not resolve. The body interprets this as something far more serious than injury. Muscles begin to respond unpredictably. Fine motor control degrades. The hand that tried to brush the ant away no longer moves with precision. It jerks, hesitates, or fails to respond entirely. This is where the phrase liquid fire stops being metaphor and becomes a crude but functional description of a neurological event. The pain does not remain static. It pulses, radiates, and intensifies in waves, as if the signal itself is alive and searching for pathways to exploit. Victims often describe it as electric, but even that falls short. Electricity implies direction and flow. This is more chaotic, like a current forced into a system that cannot regulate it, bouncing between pathways and overwhelming every attempt at control. The duration is what defines the experience. Many venomous stings deliver intense pain that fades as the body begins to process and neutralize the toxins. Bullet ant venom does not follow that pattern. The disruption of sodium channels prolongs the signal far beyond what the initial dose would suggest. Pain can persist for hours, often peaking well after the sting itself. During this time, the body is not simply enduring discomfort. It is actively struggling to regain equilibrium. Sweating increases as the autonomic nervous system responds to what it interprets as extreme stress. Heart rate can elevate. Breathing may become irregular, not because the lungs are compromised, but because the brain's control over rhythm is competing with overwhelming sensory input. In some cases, localized paralysis occurs, not from tissue damage, but from the inability of nerves to coordinate proper signals. Muscles contract and release in patterns that do not align with intention. In the dense Amazon environment, this loss of control is not a minor inconvenience. It is a vulnerability. The forest does not pause while the body recalibrates. Heat continues to press in. Insects continue to move. The ground remains uneven, layered with roots and hidden drops. A person or animal experiencing this level of neurological disruption is no longer fully capable of navigating that complexity. Balance becomes uncertain. Reaction time slows. Awareness narrows, not because the brain is shutting down, but because it is overwhelmed. From an ecological perspective, the bullet ant's strategy is remarkably efficient. It does not need to kill large predators or intruders. It needs to convince them immediately and conclusively that further interaction is not worth the cost. The intensity and duration of the sting achieve exactly that. Few animals will risk repeated exposure. Even species that are otherwise tolerant of stings or bites learn quickly to avoid areas where these ants are active. The colony, in turn, gains a protective radius not through physical barriers, but through reputation encoded in nervous systems that remember the experience. There is a broader pattern here that extends beyond a single species. In the Amazon, chemical defense often outperforms physical force. Speed, size, and strength are valuable, but they require energy and carry risk. Venom, toxin, and chemical signaling allow smaller organisms to project power disproportionate to their size. The bullet ant is not alone in this strategy, but it represents one of the most extreme examples of pain as a defensive tool. What makes it particularly effective is the way it targets the interface between body and brain. By interfering directly with nerve function, the venom bypasses many of the body's standard protective mechanisms. It does not rely on inflammation or tissue damage to create its effect. It hijacks the communication system itself. The body is still intact, but its ability to interpret and respond to its own signals is compromised. This distinction matters because it changes how the experience is processed and remembered. Pain that comes from a visible wound can be contextualized. It has a source, a boundary, and often a predictable progression. Pain that emerges from within the nervous system feels less contained. It is harder to localize, harder to anticipate, and more difficult to ignore. It demands attention in a way that few other sensations can. As the hours pass, the intensity eventually begins to subside. Sodium channels return to their normal function. Electrical signals regain their rhythm. Muscles respond more predictably. But the aftermath lingers, not just in residual soreness or fatigue, but in the memory of what the body experienced. The next time that same environment presents the same subtle cues, a particular tree base, a certain pattern of leaf litter, the response is immediate. Avoidance becomes instinctive. For the bullet ant colony, that is success. No pursuit, no prolonged conflict, no wasted energy. A single, precisely delivered event that reshapes behavior at a scale far larger than the individual interaction. In a forest where survival often depends on minimizing unnecessary risk, that efficiency is a decisive advantage. And for anything that crosses that boundary unprepared, the lesson is delivered with absolute clarity. The danger was never the size of the animal. It was the system it could disrupt. One sting, and the body is no longer entirely its own. The forest does not always present danger as motion or noise. Sometimes it gathers in places that feel abandoned, dry pockets beneath fallen logs, the undersides of broad leaves that never quite touch the ground, the hollow interiors of bark that has begun to peel away from aging trees. These are transitional spaces where humidity fluctuates and airflow slows, creating micro-environments that are neither fully exposed nor completely sealed. In the Amazon, such spaces are not empty. They are structured, occupied, and often claimed by organisms that rely on stillness and geometry rather than speed. Within one of these quiet zones, suspended between anchor points that appear incidental to the casual observer, a web stretches with deliberate asymmetry, its threads angled and tensioned in ways that reflect function rather than symmetry. At the center, or sometimes just offset from it, rests a spider of the genus Latrodectus. The body is compact, the abdomen rounded and dark, often marked on the underside with a red or orange hourglass pattern that is rarely visible from above. There is no need for display. The web does not advertise its presence, and the spider does not patrol widely. Instead, it constructs a three-dimensional tangle of silk that extends in irregular lines, some threads sticky, others purely structural. This is not the clean, radial web often associated with spiders in open spaces. It is a trap designed for cluttered environments, where prey moves unpredictably and surfaces are uneven. The silk itself is one of the most efficient biological materials in the forest. Certain strands, known as gumfoot threads, extend from the web down to the substrate, lightly attached at the base. When an insect or small arthropod disturbs one of these lines, the attachment breaks, and the elastic tension snaps the prey upward into the web structure. The spider responds not with a chase, but with a measured approach, wrapping the struggling organism in layers of silk before delivering a bite that introduces venom into its body. The process is controlled, energy efficient, and highly effective. What makes this system particularly relevant to larger animals is not its strength, but its placement. These webs are often built at heights and in locations where incidental contact is likely, just above ground level, across narrow gaps between objects, inside spaces where hands or feet might reach without full visibility. A person clearing debris, lifting a piece of wood, or steadying themselves against a trunk may pass through a web without recognizing it as a structured trap. The silk breaks easily under such force, but the contact is enough to trigger a defensive response. The bite itself is often subtle. The fangs of a black widow are small compared to those of larger spiders, and the penetration can feel like a minor pinprick or even go unnoticed in the moment. There is no immediate tearing of tissue, no dramatic injection that announces itself through pain alone. The spider does not need to deliver a large volume of venom. Its strategy relies on potency rather than quantity, and on a toxin that operates not through destruction of tissue, but through interference with the nervous system at a fundamental level. Within minutes, the character of the experience begins to shift. The venom of black widow spiders is dominated by a neurotoxic protein known as alpha-latrotoxin. This compound targets nerve terminals, particularly those involved in the release of neurotransmitters. Under normal conditions, nerve cells communicate by releasing these chemical messengers in controlled amounts, allowing muscles to contract and relax in coordinated patterns. Alpha-latrotoxin disrupts this balance by causing an uncontrolled release of neurotransmitters, effectively flooding the synaptic space with signals that the body cannot regulate. The result is not a single sensation, but a cascade. Pain emerges first, but not as a localized spike. It begins near the bite site and then expands, not outward across the skin in a simple gradient, but inward along pathways that correspond to muscle groups and nerve distributions. Muscles begin to tighten, not in response to voluntary movement, but as a direct consequence of overstimulation. This tightening can start subtly, a sense of stiffness, a mild cramp, but it does not remain contained. It builds layer by layer until the affected muscles feel as though they are being held in a constant state of contraction. This is where the liquid fire changes its form. Unlike the electric surge of the bullet ant or the deep, burning puncture of the stingray, the black widow's effect is constrictive. The body feels as though it is being drawn inward, as if invisible bands are tightening around muscle groups and refusing to release. The abdomen is often one of the first regions to reflect this change. Muscles that normally expand and contract rhythmically with breathing begin to stiffen, creating a sensation that can mimic internal injury. The chest may feel tight, not because the lungs are directly affected, but because the muscles that support breathing are no longer moving freely. Sweating increases, driven by the autonomic nervous system's response to the overwhelming neural activity. Skin becomes damp even in already humid conditions, and the body's attempts to regulate temperature become less efficient. The heart rate may rise, not solely from physical exertion or fear, but as a direct consequence of the altered neural signaling. Blood pressure can shift unpredictably. The entire system begins to operate under a new set of conditions where normal regulatory mechanisms are competing with a flood of uncontrolled input. Movement becomes difficult in a different way than with other forms of envenomation. It is not that the body cannot move, but that every movement is resisted from within. Muscles that should relax to allow motion remain partially contracted, creating a constant opposition to voluntary action. Walking requires more effort. Standing still becomes uncomfortable as muscles fatigue under sustained tension. Even small adjustments in posture can trigger waves of cramping that ripple through the body. From a physiological perspective, this sustained contraction has consequences beyond discomfort. Muscles require energy to maintain tension, and prolonged contraction can lead to fatigue, accumulation of metabolic byproducts, and increased sensitivity to further stimulation. The body is effectively working against itself, expending energy without achieving coordinated movement. Over time, this can contribute to a sense of exhaustion that compounds the immediate effects of the venom. The neurological aspect of the experience is equally significant. As neurotransmitter release becomes dysregulated, the brain receives signals that do not align with normal patterns. Pain signals overlap with motor commands, and the distinction between voluntary and involuntary action becomes less clear. The body may twitch or spasm in localized areas, while other regions remain locked in stiffness. This fragmentation of control creates a sense of internal inconsistency, where different parts of the body seem to operate under different rules. In the Amazon environment, where black widow spiders occupy niches that intersect with both forest and human-modified spaces, this form of envenomation represents a different kind of risk. It is not tied to a dramatic encounter or an obvious threat. It emerges from contact with a system that is designed to be unobtrusive. The spider does not seek confrontation. It responds only when its immediate space is disrupted. But when that response occurs, the effects extend far beyond the point of contact. Ecologically, the black widow's strategy reflects a balance between investment and return. Building and maintaining a web requires energy, but it allows the spider to capture prey without constant movement. The venom ensures that once prey is secured, it can be subdued quickly and efficiently. The same properties that make the venom effective against small animals also make it disproportionately impactful when delivered to larger ones. This is not an adaptation for defense against large predators specifically, but a consequence of a system optimized for reliability across a range of prey types. There is also an element of spatial economy in how these spiders operate. By selecting microhabitats that are stable but not overly exposed, they reduce the likelihood of disturbance while maximizing access to passing prey. These zones, under logs, within crevices, among roots, are also places that other animals use for shelter, movement, or foraging. The overlap is inevitable. The web becomes a point of intersection between different ecological roles, and the spider's presence shapes behavior even when it is not directly encountered. For animals that have experienced envenomation, the memory of that internal tightening becomes a powerful deterrent. It is not just the pain, but the loss of fluidity and movement, the sense that the body is no longer responding in a coordinated way. This memory influences future interactions with similar environments. Spaces that once seemed neutral become areas of caution. Movements become more deliberate. Contact with hidden structures is approached with increased awareness. As the effects of the venom gradually subside, the body begins to re-establish normal patterns. Neurotransmitter release returns to regulated levels. Muscles regain their ability to contract and relax in sequence. The sense of internal pressure eases, though residual soreness and fatigue may persist. Recovery is a process, not an instant shift, and during that time, the body recalibrates its expectations of movement and control. What remains is an understanding embedded not in abstract knowledge but in physical experience that not all threats in the Amazon are visible or immediate. Some are built into structures that appear incidental, hidden within the architecture of the forest itself. The black widow does not dominate its environment through size or speed. It shapes it through placement, design, and a venom that turns the body inward against itself. In the broader context of the ecosystem, this represents another variation on a common theme. the use of chemistry to extend influence beyond physical limits. The spider's reach is not defined by how far it can move, but by how effectively it can alter the systems of whatever it touches. The web captures, the bite delivers, and the venom completes the process, not by destroying, but by overwhelming the delicate balance that allows a body to function smoothly. And in that imbalance, the concept of liquid fire takes on a colder form, not a surge or a burn that spreads visibly, but a tightening, a constriction that builds quietly and then refuses to release. The body is not overwhelmed in a single moment. It is gradually enclosed by its own reactions, held in a state where movement, breath, and control are all subtly but persistently compromised. The forest changes character after dark, but not in the way most people expect. It does not become louder in any simple sense. Instead, it becomes layered, sound folding over sound, movement replacing stillness, and spaces that felt defined during the day dissolving into something less predictable. The air holds more moisture, trapping heat close to the ground, and every surface begins to glisten with condensation. Leaves sag slightly under the weight of water, bark darkens, and the thin film of humidity that coats everything turns friction into slip. It is a time when many predators rely less on speed and more on proximity, and among them is one of the few that does not anchor itself to a fixed position or web, but instead carries its threat actively through the environment. Somewhere along the forest floor, moving without urgency but with constant direction, a member of the genus Phoneutria advances through leaf litter and root networks. The name wandering spider is not a casual description. It defines the entire strategy. Unlike web-building species that invest energy into constructing traps and then waiting for prey to arrive, these spiders abandon that approach entirely. They hunt by movement, covering ground each night in search of insects, small vertebrates, and any opportunity that presents itself within reach. Their success depends not on patience, but on constant exploration combined with rapid decision-making. The body reflects this lifestyle. Long, powerful legs elevate the spider slightly above the substrate, allowing it to move efficiently across uneven terrain without becoming entangled in debris. Sensory hairs along those legs detect minute vibrations, translating the forest floor into a map of movement and pressure. Vision, while not as refined as that of some jumping spiders, is sufficient for detecting contrast and motion in low light. But the real advantage lies in responsiveness. When something enters its immediate space, the spider does not need to interpret it fully before acting. It reacts first, assesses second. During the day, these spiders often retreat into temporary shelters, under logs, within folded leaves, inside crevices in bark, or occasionally in spaces created by human activity at the forest edge. Their presence in agricultural zones and even dwellings is not a sign of preference, but of opportunity. They follow prey, and prey follows resources. In banana plantations, for example, clusters of fruit provide both shelter and food for insects, creating an environment that wandering spiders can exploit. This overlap between natural and altered habitats increases the likelihood of accidental encounters, especially when the spider is disturbed during its resting phase. The defensive posture is immediate and unmistakable. When threatened, the spider raises its front legs high, exposing the underside of its body and presenting its fangs in a display that is both warning and preparation. It is not bluffing. The strike that follows, if the threat continues, is fast enough to appear almost instantaneous. The fangs, long and capable of penetrating skin with ease, deliver venom deep into tissue in a fraction of a second. There is no prolonged engagement. The spider bites and withdraws, creating distance as quickly as it closed it. At the moment of envenomation, the sensation is sharp and localized, but that clarity does not last. Within seconds, the body begins to register something more complex. The venom of Brazilian wandering spiders is a mixture of neurotoxic peptides that interfere with ion channels in nerve and muscle cells, particularly those involved in the transmission of electrical signals. Unlike venoms that target a single pathway, this one affects multiple systems simultaneously, creating a cascade of effects that extend far beyond the initial bite site. The first shift is often a rapid intensification of pain, but not in the clean, escalating way seen with purely inflammatory reactions. Instead, the sensation becomes layered, combining sharpness with a spreading, almost electric quality that feels unstable. The nervous system is not simply signaling damage, it is being altered in how it communicates. Signals arrive faster, linger longer, and overlap in ways that the brain struggles to organize. This is where the experience begins to diverge from ordinary injury. The body does not just hurt, it feels wrong. Sweating increases, often dramatically, as the autonomic nervous system reacts to what it interprets as a significant internal disturbance. Skin becomes slick, not from environmental humidity alone, but from the body's own response. Muscles may begin to twitch or contract unpredictably, not because they are damaged, but because the signals controlling them are no longer properly regulated. Fine motor control degrades, hands may tremble. Movements that require coordination become imprecise. The cardiovascular system is also drawn into the response. Heart rate can accelerate, sometimes significantly, as the body attempts to compensate for the perceived stress. Blood pressure may fluctuate. Breathing can become shallow or irregular, not because the lungs are compromised directly, but because the neural control of respiratory rhythm is being influenced by the same disrupted signaling that affects other systems. The result is a sense of internal instability, a feeling that the body is no longer operating as a unified system, but as a collection of parts responding independently to conflicting instructions. In some cases, the effects extend into more unusual territory. The venom of certain Phonutria nigriventa populations contains components that influence nitric oxide pathways, leading to prolonged vasodilation. This can result in symptoms such as sustained, involuntary muscle responses in specific regions of the body, including conditions that are physiologically significant and medically notable. While not the primary danger, these effects illustrate the breadth of the venom's impact. It is not limited to pain or paralysis. It interacts with multiple biochemical systems, creating a complex and sometimes unpredictable profile. From an ecological standpoint, this broad-spectrum effect serves a clear purpose. The spider does not specialize in subduing a single type of prey. It encounters a wide range of organisms, each with different defenses and physiologies. A venom that disrupts multiple systems increases the likelihood of quickly incapacitating whatever it bites, whether it is an insect, an amphibian, or a small mammal. Speed is critical. The spider cannot afford a prolonged struggle that might attract predators or allow prey to escape. For larger organisms, including humans, this same strategy translates into a disproportionate response. The dose delivered in a defensive bite is not calibrated for a large body. It is simply the amount required to ensure effectiveness against typical prey. But because the venom targets fundamental processes, ion channels, neurotransmitter release, vascular regulation, the effects scale in a way that is felt throughout the body. The psychological component of this experience should not be underestimated. As the body begins to behave unpredictably, the brain attempts to interpret what is happening. The combination of intense pain, involuntary muscle activity, and autonomic responses creates a feedback loop of stress. Awareness narrows, not because of external distraction, but because internal signals dominate attention. The environment recedes. The focus turns inward, tracking sensations that do not align with normal expectations of how the body should function. In the Amazon, this inward shift can be dangerous. The forest demands constant awareness of terrain, obstacles, and other organisms. Losing that external focus, even briefly, increases the risk of secondary incidents, missteps, falls, or encounters with other hazards. The wandering spider's venom does not need to immobilize completely to create vulnerability. It only needs to disrupt enough control to make the environment harder to navigate. What makes this interaction particularly striking is the contrast between the spider's size and the scale of its effect. It is not a large animal by Amazon standards. It does not rely on overwhelming force or physical dominance. Its power lies entirely in chemistry and delivery. A single rapid bite initiates a chain of events that unfolds over minutes and can persist for hours, depending on the severity of envenomation and the response of the individual. Recovery, when it occurs without complication, involves the gradual restoration of normal neural function. Ion channels return to their standard behavior. Neurotransmitter release stabilizes. Muscles regain coordinated control. But this process is not instantaneous. The body must process and clear the venom components, and in the meantime, the residual effects can linger: fatigue, localized pain, and a heightened sensitivity to stimuli. From the spider's perspective, the encounter is already over. It has retreated, blending back into the forest floor, continuing its movement through a landscape that it navigates with constant, low-level awareness. It does not track the outcome of its bite. It does not need to. The strategy is complete the moment distance is re-established. There is a broader lesson embedded in this interaction, one that aligns closely with the underlying theme of liquid fire. In the Amazon, danger is not always defined by visible force or immediate destruction. Sometimes it is defined by the way a system can be altered from within, how a small amount of venom can shift the balance of control inside a much larger body. The wandering spider does not overwhelm its environment. It exploits the fundamental mechanisms that all complex organisms rely on to function. In doing so, it demonstrates a form of efficiency that is both subtle and profound. It does not need to be seen often to be effective. It does not need to engage frequently to maintain its role. Its presence is enough, embedded in a network of interactions that shape behavior across species. Animals learn to avoid certain spaces, certain textures, certain disturbances, not because they constantly encounter the spider, but because the cost of a single mistake is so high. And when that mistake does happen, the experience is not defined by a single moment of contact, but by the cascade that follows. Pain that spreads, control that slips, systems that misfire, each element reinforcing the idea that the body is no longer entirely predictable. The forest, in that moment, has not changed. It remains as it was, dense, humid, and full of life. But the relationship between the organism and that environment has shifted, shaped by a venom that turns internal stability into something uncertain and transforms a brief encounter into a prolonged, systemic event. The forest floor is often described as a layer, but that description is misleading. It is not a surface you move across. It is a volume you move through. Beneath every step lies a shifting architecture of decomposing leaves, fungal networks, burrows, and moisture gradients that change by the hour. What appears flat is, in reality, stacked, thin strata of life and decay, compressing and expanding under pressure. In that compressed darkness, where light rarely penetrates and airflow is minimal, something moves with a form that does not resemble anything vertebrate. It does not step so much as flow, each segment contributing to a coordinated wave that pushes the body forward with unsettling precision. Emerging from beneath a slab of damp bark, a giant centipede, Scolopendra gigantea, slides into a narrow band of filtered light. Its body is long, segmented, and lacquered in alternating tones of deep brown, amber, and near black, each segment supporting a pair of legs that articulate independently yet move in synchronized patterns. The motion is not chaotic. It is controlled, efficient, and deceptively fast when needed. At rest, the centipede appears almost ornamental, its many limbs arranged in symmetry that suggests fragility. In motion, that illusion collapses. The legs become a conveyor system, gripping and releasing the substrate in rapid succession, allowing the animal to traverse uneven terrain with a stability that larger, fewer-limbed creatures cannot match. This is a predator built for proximity. Unlike animals that rely on distance, vision, pursuit, or ambush from concealment, the centipede operates within immediate reach. Its sensory system is distributed along its body, with antennae at the front probing the environment constantly, sampling chemical cues and physical contact. It does not need to see far ahead. It needs to understand what is directly in front of it, within the span of a few centimeters. Prey is detected not as an image, but as a presence, movement, vibration, the subtle displacement of air or substrate. When contact occurs, the response is instantaneous and mechanical. The front segments lift slightly, and the first pair of legs, modified into specialized appendages known as forcipules, arc forward. These are not legs in the conventional sense, but venom delivery structures, curved and sharpened, connected to glands that produce a potent mixture of toxins. The centipede does not strike from a distance. It closes the gap entirely, anchoring its body with the rear legs while the front locks onto the target. The anchoring is critical. The many legs along the body press into the substrate, creating multiple points of contact that stabilize the animal during the strike. This is not a fleeting interaction. The centipede commits fully, using its entire body as a brace. The forcipules puncture, delivering venom directly into tissue, and for a brief moment, the animal maintains contact, ensuring that the injection is complete. Then, just as quickly, it releases and withdraws, its body reversing or redirecting with the same fluid coordination that brought it forward. The encounter is over in seconds. The effect is not. The initial sensation is immediate and unmistakable, a sharp, penetrating pain that establishes a clear point of contact. But unlike injuries that remain localized, this sensation begins to change almost as soon as it is registered. The venom of Scolopendra species contains a complex mixture of compounds, including neurotoxins, cytotoxins, and enzymes that affect both nerve signaling and surrounding tissue. The purpose is not to paralyze instantly in all cases, but to overwhelm the prey's ability to respond effectively, creating a window in which the centipede can maintain control or allow the venom to take effect. In a larger organism, this translates into a layered experience. The pain intensifies rapidly, but it does not remain sharp. It deepens, broadens, and takes on a quality that is both burning and electric, as if the initial puncture has opened a pathway for something to spread beneath the skin. The area around the bite begins to swell, not only from mechanical damage, but from the body's inflammatory response to the venom. Blood vessels dilate, increasing flow to the region, and immune cells begin to accumulate, attempting to contain and process the foreign compounds. This is where the sensation becomes more complex. The swelling creates pressure within the tissue, compressing nerve endings and amplifying the signals they send. At the same time, the neurotoxic components of the venom interfere with normal nerve function, causing signals to misfire or persist longer than they should. The result is a feedback loop. Chemical irritation increases nerve activity, and increased nerve activity heightens the perception of irritation. Movement becomes difficult, not because of structural damage alone, but because the body is reacting to conflicting information. The brain receives intense signals from the affected area and attempts to interpret them as both injury and threat. Muscles surrounding the site may contract involuntarily, creating stiffness or localized spasms. If the bite occurs on a limb, that limb may feel both hypersensitive and uncooperative, responding to commands with hesitation or exaggerated movement. The centipede, meanwhile, is no longer present. It has already moved on, its role in the interaction complete. This separation between cause and effect is part of what makes the experience so unsettling. The source of the injury is gone, but the process it initiated continues to unfold within the body, independent of any further external input. From an ecological perspective, this efficiency is essential. The centipede is a generalist predator capable of subduing a wide range of prey, from insects and spiders to small vertebrates such as frogs, lizards, and even juvenile mammals or birds. Its venom must be versatile, effective across different physiologies, and capable of producing rapid results. At the same time, the centipede must minimize its own risk. Prolonged sangharsh with struggling prey increases the chance of injury or exposure to predators. A quick strike, followed by withdrawal, reduces that risk while still ensuring that the prey is compromised. There is also a structural advantage in the centipede's design that supports this strategy. The segmented body allows for flexibility and resilience. If part of the body encounters resistance or obstruction, the rest can adjust, maintaining forward motion or retreat without losing overall coordination. This adaptability extends to how the animal interacts with its environment. It can climb, burrow, and navigate complex three-dimensional spaces with relative ease, accessing niches that are unavailable to less flexible organisms. The forest floor, with its constant turnover of organic material, provides an ideal setting for such a creature. Decomposition creates both food sources and shelter, attracting a variety of smaller organisms that serve as prey. At the same time, the dense structure of leaf litter and debris offers protection from larger predators. The centipede exists within this matrix, rarely exposed for long, its movements largely hidden from view. For the organism that experiences the bite, the aftermath is defined by persistence. The pain does not resolve quickly. It lingers, fluctuating in intensity, but rarely disappearing entirely in the short term. Swelling may increase over time, extending beyond the immediate site as the inflammatory response spreads. In some cases, systemic symptoms can develop: headache, nausea, or generalized discomfort, reflecting the body's broader reaction to the venom. The sensation of heat remains a dominant feature, but it is not uniform. It pulses, intensifies, recedes slightly, and then returns, as if the body is repeatedly rediscovering the injury. This variability makes it difficult to adapt or ignore. Just as the brain begins to accommodate the sensation, it shifts, drawing attention back to the affected area. There is also an element of tactile distortion. The skin around the bite may feel different, tight, sensitive, or even numb in patches, as nerve function is altered by both chemical and mechanical factors. Touching the area can produce exaggerated responses, with even light contact triggering sharp discomfort. This hypersensitivity reinforces the body's protective behavior, discouraging further use of the affected region. In the context of the Amazon, where movement is constant and conditions are demanding, this lingering impairment has practical consequences. A person or animal dealing with such an injury must navigate terrain that does not accommodate hesitation. Roots, uneven ground, and dense vegetation require coordinated movement and balance. The inability to use a limb normally, combined with persistent pain, increases the risk of missteps and secondary injuries. From a broader biological perspective, the centipede's venom represents another variation on a common theme: the use of chemical means to extend influence beyond physical contact. The animal does not need to remain engaged to maintain its effect. The venom continues to act, interacting with the body's systems in ways that outlast the initial encounter. This allows the centipede to operate efficiently within its ecological niche, conserving energy while still achieving its objectives. What distinguishes this final chapter is its intimacy. The centipede does not strike from a distance or rely on concealment alone. It engages directly, its many legs and flexible body bringing it into close contact with its target. The attack is not abstract or distant. It is immediate, physical, and anchored in the mechanics of touch and pressure. This proximity makes the resulting sensation feel more personal, more contained within the body, even as it spreads. As time passes, the body begins to recover. The venom is gradually broken down or neutralized, and normal physiological processes reassert themselves. Swelling decreases, nerve signals return to baseline patterns, and movement becomes less restricted. But this recovery is not instantaneous, and during the period in which it unfolds, the individual carries the experience forward, step by step, through an environment that does not pause or simplify. In the end, the centipede leaves behind more than a wound. It leaves behind a state, a condition in which the body is altered, forced to operate under strain and uncertainty. The animal itself is no longer present, but its influence remains, embedded in the tissues and systems that continue to respond to its venom. This is the final expression of liquid fire within the Amazon. Not a single moment of impact, but a sustained internal presence. A heat that is not external, not visible, but carried within the body long after the source has disappeared. In a forest defined by constant interaction and hidden complexity, it is a reminder that the most enduring effects are often the ones that continue unseen, shaping movement, perception, and behavior from the inside out. The forest does not always announce danger with movement or sound. Sometimes it presents it as pattern, clean, deliberate, and almost too precise to belong to something harmless. Along the dim edges of the Amazon understory, where filtered light breaks into narrow bands across leaf litter, a sequence of color interrupts the dominant greens and browns. Red, black, yellow, arranged in rings that appear almost artificial in their clarity. It is not camouflage. It is the opposite, a signal designed to be seen, but only by those who understand what it means. Moving through that filtered light is a slender snake of the genus Micrurus. Its body is narrow, its head only slightly distinct from its neck, its movements controlled and unhurried. There is no display of aggression, no widening of posture, no attempt to appear larger than it is. The coral snake does not rely on intimidation through size or speed. It relies on recognition, an evolutionary contract written in color. For many predators, those bands are enough. The message is simple: this is not worth the risk. But the effectiveness of warning coloration depends on memory and experience. In regions where multiple species share similar patterns, some harmless and some not, that message can become blurred. Evolution has produced mimics, non-venomous snakes that imitate the coral snake's coloration to gain protection without the cost of producing venom. This creates a system where recognition is valuable but not always reliable. For a predator or an unwary intruder, hesitation becomes a gamble, and misinterpretation can carry consequences that are not immediately obvious. The coral snake itself avoids confrontation whenever possible. It spends much of its time concealed beneath leaf litter, within loose soil, or inside the hollow spaces created by decaying vegetation. Its body is built for this kind of movement: smooth scales that reduce friction, a narrow profile that allows it to slip through tight spaces, and a musculature adapted for steady, controlled progression rather than explosive bursts of speed. It feeds primarily on other small, elongated animals, snakes, lizards, and occasionally amphibians, subduing them with a venom that acts not by overwhelming force, but by interrupting the most fundamental processes of life. When a bite occurs, it is often the result of direct contact, an accidental step, a hand placed without full visibility, or an attempt to handle what appears to be a small, manageable animal. The coral snake does not strike with the same speed or range as some larger vipers. Its fangs are relatively short and fixed at the front of the mouth, and delivering venom can require a more sustained contact. In some cases, the snake may hold on briefly, chewing to ensure that venom is introduced into the tissue. This method is less dramatic than a rapid strike, but it is effective in its own way. The initial sensation of the bite is frequently underwhelming. There may be a slight prick, a mild discomfort that does not immediately signal the seriousness of what has occurred. There is often little swelling, little visible damage. The skin may show small puncture marks, but nothing that suggests a major injury. This is where the danger begins to diverge from expectation. In an environment where many threats announce themselves through pain or visible trauma, the absence of immediate intensity can lead to underestimation. The venom of coral snakes is primarily neurotoxic, composed of compounds that interfere with the transmission of signals between nerves and muscles. Specifically, these toxins target the neuromuscular junction, the point where a nerve communicates with a muscle fiber to initiate contraction. Under normal conditions, a nerve releases a neurotransmitter that binds to receptors on the muscle, triggering a response that results in movement. Coral snake venom disrupts this process by blocking those receptors, preventing the signal from being received. At first, this disruption is subtle. Minutes pass, and the body begins to register small changes. There may be a slight tingling near the bite site, a sensation that is easy to dismiss or attribute to minor irritation. Muscles in the immediate area may feel weak or unresponsive, but the effect is localized and not yet alarming. Movement is still possible. Coordination remains largely intact. The forest continues to move around the individual, unchanged, indifferent to the internal shift that has begun. As time progresses, the pattern becomes clearer. The weakness does not remain confined. It spreads, not outward across the skin, but along functional lines. Muscle groups that share neural pathways begin to exhibit similar symptoms. The hand that was used to brush away the snake may feel less precise, fingers responding with a slight delay. The arm may feel heavier, as though the effort required to move it has increased. These changes are not accompanied by intense pain. They are quiet, almost methodical. This is the liquid fire in its most deceptive form. There is no burning sensation in the traditional sense. Instead, there is a gradual loss of control, a creeping absence where responsiveness should be. The body is not overwhelmed by sensation, but by the lack of it. Signals that should pass cleanly from nerve to muscle begin to fail. The brain sends commands that do not result in expected actions. Muscles that should contract remain still or respond weakly. The coherence of movement begins to fragment. The autonomic nervous system, which controls involuntary functions such as breathing and heart rate, is also part of this network. As the venom continues to interfere with signal transmission, these systems can become affected. Breathing, which relies on coordinated contraction of the diaphragm and intercostal muscles, may become shallow or labored. At first, this may feel like fatigue or mild shortness of breath, but as the disruption increases, the effort required to draw a full breath can grow, creating a sense of internal resistance. This progression is what defines the coral snake's danger. It is not the immediate impact of the bite, but the delay, the gap between cause and effect that allows the situation to evolve quietly. The body continues to function, but with decreasing efficiency. Each system remains operational, but less reliable. The individual is not incapacitated in a single moment, but gradually becomes less capable of responding to the environment. In the Amazon, where terrain is complex and conditions are demanding, this loss of function has broader implications. Navigation requires coordination. Balance depends on precise muscle control. Awareness must be maintained across multiple sensory inputs. As these abilities degrade, the environment becomes more difficult to manage. A path that was previously straightforward becomes a series of obstacles. A river crossing becomes more dangerous. Even maintaining a stable posture can require effort that the body is no longer equipped to provide. From an evolutionary perspective, the coral snake's strategy is highly specialized. Its venom is not designed to cause immediate trauma, but to ensure that prey cannot escape once envenomation has occurred. Small animals that rely on rapid movement are effectively neutralized as their muscles lose the ability to respond. The snake does not need to pursue aggressively. It can wait, tracking the prey until the effects of the venom take hold. This approach minimizes risk. By reducing the need for prolonged sangharsh or repeated strikes, the coral snake conserves energy and avoids exposing itself to potential predators. Its bright coloration further reduces the likelihood of being attacked, creating a system where both offense and defense are optimized for efficiency rather than spectacle. There is also a broader ecological role embedded in this behavior. By preying on other small reptiles and amphibians, coral snakes help regulate populations within the understory, contributing to the balance of species interactions. Their presence influences the behavior of both predators and prey, shaping movement patterns and habitat use in subtle ways. Even species that do not directly interact with the snake may alter their behavior in response to the risk it represents. As the effects of the venom continue to develop, the body reaches a point where the loss of control becomes unmistakable. Muscles that were once responsive now fail to act reliably. Simple tasks require concentration and effort. Breathing may become the central focus, as the body prioritizes maintaining oxygen intake despite the growing difficulty. The experience is not one of sudden collapse, but of gradual encroachment, a narrowing of functional capacity that feels both internal and inescapable. Recovery, when it occurs with appropriate intervention, involves the gradual restoration of neuromuscular communication. The toxins must be neutralized or cleared, allowing receptors to function normally again. This process takes time, and during that time, the body must be supported to ensure that critical functions, particularly respiration, are maintained. Without such support, the consequences can be severe. What remains after recovery is not just physical memory, but an altered understanding of risk. The coral snake does not rely on overwhelming force or immediate pain to assert its presence. It operates through delay and subtlety, allowing its venom to act over time rather than in a single moment. This makes it one of the most quietly effective threats in the Amazon, a reminder that not all danger is loud and not all suffering announces itself clearly. In the context of liquid fire, this chapter represents a shift from intensity to persistence. The fire is not a blaze that consumes instantly, but a slow internal process that spreads through systems that are essential to life itself. It is the kind of danger that does not end when the encounter is over, but continues to unfold, revealing its full impact only as time passes and the body begins to lose the ability to govern itself. And in a forest where survival often depends on immediate recognition and rapid response, that delay, quiet, methodical, and deeply internal, can be the most dangerous element of all. The river does not look dangerous at first contact. In the Amazon's floodplains, water spreads wide and shallow during seasonal expansion, slipping quietly into forests and over sandbanks until the boundary between land and river dissolves into a single, reflective surface. Sunlight penetrates easily here, illuminating suspended particles of silt that drift like dust in slow motion. The bottom appears soft, almost inviting. Fine sediment layered over packed clay, broken occasionally by roots and submerged debris. It feels like a place built for crossing, not confrontation. But this is precisely where one of the most deceptive hazards in the system waits without movement, without outline, and without any need to reveal itself. Buried just beneath that thin skin of silt, a freshwater stingray, most often a member of the genus Potamotrigon, lies perfectly still. Its body is a flattened disc, pressed flush against the substrate, edges slightly undulating with subtle respiratory movements. The dorsal surface is patterned in mottled browns and muted blacks, mirroring the exact texture and tone of the riverbed. Within seconds of settling, the animal becomes visually indistinguishable from its surroundings. Fine sediment settles over its back, softening any remaining contour. Only the eyes and spiracles remain exposed, positioned on top of the body, where they can monitor both water flow and overhead disturbance. From above, there is no obvious sign that anything alive occupies that space. This is not passive concealment. It is an active survival strategy shaped by both predation and avoidance. Freshwater stingrays in the Amazon are not apex predators, but they are efficient benthic hunters, feeding on small fish, crustaceans, and invertebrates that move along the riverbed. Their sensory system is tuned to detect electrical signals, minute bioelectric fields produced by muscle contractions in nearby organisms. Even when prey is buried or hidden, these rays can locate it with remarkable precision. The same system that allows them to hunt also makes them acutely aware of approaching disturbances. A large animal entering the water, displacing sediment and altering pressure patterns, is immediately detected. But unlike many fish that respond with rapid escape, Stingrays often remain still. Movement would reveal them. Stillness keeps them hidden. The danger emerges not from aggression, but from this refusal to move. A foot steps down into the silt. The surface gives way slightly, compressing under weight. For a fraction of a second, nothing happens. Then the riverbed erupts upward in a controlled, explosive motion. The stingray does not turn to face the intruder. It does not need to. Its tail, long and muscular, whips forward in a precise arc over its own body. Embedded along that tail is a rigid spine, serrated, sharp, and coated in a sheath of venom-producing tissue. The spine drives upward with enough force to penetrate deeply, often entering the foot, ankle, or lower leg of whatever has stepped onto or too close to the ray. The mechanics of the strike are brutally efficient. The spine is not smooth. It is lined with backward-facing barbs that anchor it in tissue once it penetrates. As it enters, the surrounding sheath tears, releasing venom directly into the wound. When the tail retracts, those barbs can tear further, widening the puncture and embedding fragments of tissue deeper inside. This is not a clean injury. It is a complex, invasive wound that combines mechanical damage with chemical assault. The initial sensation is immediate and unmistakable. It begins as a sharp, localized puncture, but within seconds, that point of contact transforms into something far more intense. The venom of freshwater stingrays contains a mixture of enzymes and proteins that affect both nerve tissue and surrounding cells. Unlike venoms that target specific systems with precision, this is a broad-spectrum irritant designed to cause maximum disruption at the site of entry. Pain receptors are activated and then amplified, not just by the toxin itself, but by the body's own inflammatory response. What follows is not a simple escalation, but a spreading event. The pain does not remain confined to the wound. It radiates outward, moving through surrounding tissue in waves that feel hot, deep, and difficult to localize. It is often described as burning, but that term fails to capture the layered nature of the sensation. There is heat, yes, but also pressure, throbbing, and a persistent invasive quality that makes it feel as though something is actively moving beneath the skin. The body interprets this as a severe injury, and it responds accordingly. Blood vessels dilate, increasing flow to the area. Swelling begins almost immediately, tightening the surrounding tissue and further amplifying nerve signals. Standing becomes difficult within moments. The foot or leg that absorbed the strike no longer functions normally, not because of structural failure, but because the pain overrides the brain's ability to coordinate movement. Weight shifts instinctively away from the injured area, but in shallow, unstable terrain, that shift can lead to imbalance. The riverbed is uneven, layered with soft patches and hidden obstacles. A person or animal attempting to move quickly through this environment while managing intense pain is at a significant disadvantage. Each step becomes a calculated risk, and the urgency to escape the water competes with the body's inability to move cleanly. The wound itself continues to evolve. The mechanical damage from the spine creates a deep puncture that is difficult for the body to isolate. Unlike surface injuries that can be cleaned and monitored visually, this penetration extends into muscle and connective tissue, carrying venom with it. The enzymes within the venom begin to break down cells, contributing to tissue damage that can persist long after the initial strike. In some cases, fragments of the spine or sheath remain embedded, acting as foreign bodies that prolong inflammation and increase the risk of infection. The sensation of heat intensifies as the body's immune response accelerates. White blood cells flood the area, attempting to contain both the toxin and any introduced pathogens. This response is necessary, but it also contributes to the feeling of internal pressure and burning. The wound becomes a focal point for multiple overlapping processes: nerve activation, chemical irritation, immune defense, and mechanical disruption. The result is a complex, sustained experience that does not resolve quickly. In the Amazon, where water temperatures are warm and microbial life is abundant, the risk associated with such a wound extends beyond immediate pain. The river is not sterile. It carries bacteria, parasites, and organic material that can enter the body through any break in the skin. A deep puncture created by a stingray spine provides direct access to internal tissue, bypassing many of the body's external defenses. Without proper care, infections can develop, complicating recovery and extending the period of impairment. From the perspective of the stingray, however, none of this is intentional in the way humans might interpret it. The strike is purely defensive. The animal has no interest in pursuing or subduing large intruders. Its entire strategy is based on remaining undetected. When that fails, the response is immediate and decisive, designed to create enough deterrence that the threat does not return. The energy cost of such a strike is relatively low compared to sustained escape or confrontation. One rapid movement, one delivery of venom, and the interaction is over. This efficiency is critical in an environment where visibility is limited and encounters are often accidental. The river does not allow for long-distance assessment. Sediment clouds easily obscuring vision. Sound travels differently underwater, distorted by currents and obstacles. Chemical cues disperse slowly. In such conditions, the ability to respond instantly to contact is more valuable than the ability to anticipate it from afar. There is also an ecological balance at play. Freshwater stingrays occupy a niche that connects the riverbed to the broader food web. They regulate populations of smaller organisms and, in turn, are preyed upon by larger predators such as caimans. Their camouflage and defensive capabilities allow them to maintain this role without constant exposure to predation. The venomous spine is not just a weapon. It is a tool that enables them to exist in a space where both vulnerability and opportunity are constant. For the organism that receives the strike, the experience reshapes behavior almost immediately. The memory of that spreading internal burn becomes associated not just with the animal itself, but with the environment that concealed it. Shallow water, once perceived as safe, becomes a zone of caution. Steps are placed more carefully, movements slow. Awareness shifts downward, scanning for subtle disturbances in sediment or unnatural patterns in the riverbed. This behavioral adjustment is not unique to humans. Many animals that share these waters learn similar lessons through experience or instinct. Some species develop specific movement patterns, shuffling feet along the bottom rather than stepping directly, to reduce the likelihood of triggering a defensive strike. This technique, sometimes referred to as the stingray shuffle, creates vibrations that encourage buried rays to move away before contact occurs. It is a simple adaptation, but one that reflects a deeper understanding of how these animals operate within their environment. The river, in this sense, becomes a place of negotiated movement. It is not about eliminating risk, but about reducing the chance of sudden, invisible contact. Every step carries information, both given and received. Pressure waves travel through water and substrate, signaling presence. The stingray reads those signals and decides whether to remain hidden or to act. Most of the time, stillness prevails. The strike is a last resort, triggered only when concealment fails and contact is unavoidable. But when it does happen, the effect is disproportionate to the size and intent of the animal. A single defensive motion transforms a routine crossing into a prolonged physical crisis. The pain does not end at the moment of contact. It expands, deepens, and persists, turning the body's own systems into amplifiers of the initial event. Movement becomes negotiation. Stability becomes uncertain. And the simple act of standing, something rarely considered, becomes a challenge shaped by a wound that continues to assert itself from within. In a landscape where water hides as much as it reveals, the stingray embodies a specific kind of threat, one that does not chase, does not pursue, and does not announce itself. It waits, perfectly integrated into its environment, until the boundary between safety and contact is crossed. Then, in a single, efficient motion, it delivers a lesson that lingers far beyond the river's edge, a reminder that in the Amazon, the most enduring pain is often the kind that does not stay where it started.